Welcome back to the Green Chemistry Education webinar series hosted by the Green Chemistry Commitment. My name is Amy Cannon. I'm the Executive Director of Beyond Benign, a nonprofit organization dedicated to green chemistry education in K through 12 through higher ed. This webinar series is designed to highlight relevant topics in green chemistry education for faculty and students who are looking to adopt green chemistry in their courses and programs. As a reminder, we are broadcasting live and recording this session, so all attendees are in listen-only mode. So if you have a question, just type it right in there on your control panel into the question and chat box, and we will take a look at them and we'll respond to as many questions as we can after Dr. Kostal's presentation. The recording will be posted on the link that you see in the welcome box and also on this slide here. And any supporting documents such as the PowerPoint slides, the presentation slides will also be posted on that link as well. And you'll see my note, we are taking the summer off for webinar series because there's a lot going on in the summer for everyone goes in their different directions. So we look forward to updating you and letting you know what we have coming in the fall. For those of you who participate in social media, please connect with us on Twitter or Facebook. We'd love to hear some live tweeting going on out there. So thank you so much for joining in and for taking part in the discussion. So like I said, this webinar is being brought to you as part of the Green Chemistry Commitment Program, which is a consortium program aimed at transforming green chemistry education. And the program is a voluntary, flexible program for adopting green chemistry student learning objectives and for promoting the work that you are currently doing at your institution that can serve as models for other institutions to get involved. So you can find more information right on our website, posted here, or you can email me directly. As part of the webinar series, we give away a green chemistry book at the conclusion of each webinar. So we announce a randomly selected winner from our list of attendees and at the end of each webinar, and we will send an email to you immediately after, and we'll get that book right out to you. All right. So with that, I would like to introduce our speaker, Dr. Jakub Kostal. Dr. Kostal is an assistant professor at the Chemistry Department and Computational Biology Institute at George Washington University. His research focuses on the application of computational chemistry to the de novo design of safer chemicals and the development of predictive tools for different toxicological endpoints. Through collaborations with experimental toxicologists and organic chemists, he is developing methodology akin to computational drug design for the de novo design of functional chemicals with minimal biological activity. That sounds fantastic. Dr. Kostal obtained his BS in chemistry and biochemistry from Middlebury College and completed his graduate work at Yale University with Bill Jorgensen in theoretical and biophysical chemistry. And since then, he has served as CSO in Sustainability A to Z, a green chemistry consulting firm, and as founder and CEO of Designing Out Toxicity Consulting, LLC, a company that commercializes state-of-the-art tools for predicting chemical hazard. So we're really excited to have Dr. Kostal speak to us today about what they are working on there at George Washington University with their programs and courses. So with that, I am going to hand the controls over to you, Jakub. So there you go.
All right, thank you, Amy. Thank you for the introduction. Let me just load up these slides.
Looks great.
Looks perfect. Okay, great. Terrific. So I'm very happy to be here to advertise our newly designed and developed master's program in environmental and green chemistry at George Washington University that will be starting this coming fall, 2016. So our program offers advanced training for bachelor graduates in really the fundamentals of physical sciences that are underlying the environmental challenges that we face today. The degree is designed to mostly attract recent college graduates, but we also aim at professionals, technical workers, and policy personnel who have interest in the nexus of chemistry, sustainability, and environmental science. Now, when putting this program together, we wanted to accomplish two things. One was to build a unique program that combines environmental and green chemistry, and among other things, teaches how to design new chemicals that are both safe and functional, so they retain their intended functionality. And two, to be more pragmatic, structure the program so that its graduates find suitable jobs, jobs that will matter to them and will matter to society at large. I find that there's often disconnect between sort of the perceived freedom of choice in academic explorations and the needs of the job market. So in designing this master's course, we really wanted to avoid this pitfall. And for that reason, we worked with folks at EPA and NIEHS and other agencies in DC to make sure that we are creating something that is needed, that fills a gap in the market. Now, in the big picture, we know that there is growing public awareness about the state of our environment, and chemical product safety and new chemical regulatory policies have really been driving demand for employees trained in environmental and green chemistry, and not just for experts in the current practices, but really for professionals that can lead the progress in the field. And one only has to look at industrial leaders and trendsetters like Google, Apple, Hewlett-Packard, or Unilever, who are putting increased emphasis on developing products with high standards for safety and for sustainability as well. And all these companies have been massively hiring trained professionals to accomplish these goals, to change the industry really from within. And just as a curiosity, I checked this morning, and just on LinkedIn alone, there was a posting of 288 jobs, green jobs, for Google alone. I mean, if I look at titles like what positions like sustainability officer or manager. 10 years ago, we wouldn't hear titles like this. So I feel like it's the landscape of environmental responsibility that's constantly shifting, and our master's program is really aimed to respond to this change and to put the right people in the right places in both industry, government, and academia to move the field forward. Now, as far as the program's location, again, George Washington University is based in Washington, D.C., and according to BLS, the Bureau of Labor and Statistics, D.C. offers one of the highest percentages of private sector jobs in what's called green goods and services in the nation. And of course, that entails much more than what this program focuses on, but it's a good location, good place to be. And if we consider both private sector and public sector, then I think DC ranks second highest or highest in the nation in terms of the jobs that are available within the green space. So, bottom line, I think we do believe that we have something unique here with the master's program, and something that will provide solid career tracks for the graduates when they look for jobs, whether it's in the DC area or in the US in general. Now, just to go into more specifics, the master's program is 1.5 years. It's a 30 credit hour program that basically addresses two what we think are complementary areas. One is evaluating the state of our environment, and two is developing and assessing greener technologies that have or have potential positive environmental impact. So while environmental chemistry can be considered instrumental in really providing the necessary appreciation for studying the impact of humans on ecosystems, green chemistry advocates the design of new chemicals or the redesign of existing chemicals and chemical processes to have minimal environmental impact. So the way we look at it, there is this natural complementarity between these two focus areas, and then that's really what we structured this program around. So unlike many existing graduate and certificate programs in environmental science, and there are many of these around the country, our coursework is interdisciplinary and emphasizes the basic underlying science and the emerging applications that lie at the nexus of green chemistry and environmental chemistry. The program has 5 core focus areas. It's renewable energy, or energy and the environment, environmental analytical chemistry, air, water, and soil chemistry, and then green chemical processing and chemical toxicology, which encompasses also the design of safer chemicals. We also plan for the program to leverage elective courses from public health, science policy, engineering, and business administration coursework to really provide a broader perspective and strengthen the students' communication and interpersonal skills. So they have a sort of a broader background in terms of how to approach people from various backgrounds as well, and deliver their scientific expertise, whether it's during the program or probably more importantly after they graduate. So the coursework is flexible, and it's really built around students' personal needs and goals. This is something that's very common in master's programs at GW, and I suspect DC schools at large, since many of the participants are expected to be working professionals. So all the courses take place either early or late evening, allowing those that have day jobs to take part in this program. We're also, for future, we are toying with the idea of offering all the proposed coursework or part of it as sort of a hybrid program that utilizes both regular classwork, so attending physical classes and having online classes, so that we allow some of the people who might be commuting to lower their costs towards the program. I personally am not a huge fan of this approach, but there is a clear, undeniable advantage that, and it may attract people that would otherwise be steered away from attending this program. Lastly, the program is housed by our chemistry department here at GW, so it's very much rooted in chemistry. As much as we have many electives from the other schools, like I mentioned at GW, the focus is on the fundamental science and chemistry specifically that underlines environmental chemistry and green chemistry strategies and approaches. We have 6 core faculty members that are dedicated to this program, but we have lined up other faculty at GW who are affiliated with the program, along with some folks at EPA and other agencies and academic institutions in the area like Georgetown University, Howard University, University of Maryland, to provide additional expertise. Again, this program is starting this coming fall, so this is a brand new thing, so naturally there's still a lot of things that we are tinkering with and things that will sort of settle in their place as we go along. Now, I thought that what would be beneficial for this webinar is to go a little bit into the core courses that the program offers. Again, there are a host of electives, and I can provide some materials and links at the end of this presentation that can give you a more comprehensive review of what's available and how one can structure and design its own path within this master's course. But it's these core courses that everything really rests on, so I would go into a little more detail here. So the first course is one that covers the fundamentals of energy conversion in thermochemical, thermomechanical, electrochemical, and photoelectric processes in both existing and future power and transportation systems, with really emphasis on efficiency, environmental impact, and performance. So systems that utilize fossil fuels, hydrogen fuel, nuclear, renewable sources over a range of sizes and scales are discussed in this course. The applications include fuel reforming, hydrogen and synthetic fuel production, fuel cells and batteries, combustion of fossil fuels and bio-derived fuels, hybrids, catalysis, supercritical and combined cycles, photovoltaics, and so on. The course also deals with different forms of energy storage and transmission, and optimal source utilization and fuel life cycle analysis. Houston Miller is our faculty who designed and teaches this course, so I encourage those who would like to get more details on this specific course to reach out to him. I'm including his contact at the bottom of this slide. The second course that we have is in environmental analytical chemistry, which introduces the students to the specialization in advanced modern analytical methodology that meets the needs of environmental assessment. So the course focuses on analytical instrumentation, techniques for remote measurements, determination of trace atmospheric constituents of anthropogenic and natural origin, conducting uncertainty analysis, detection and identification of organic and inorganic pollutants in air, water, and soil and biota, and the determination of heavy metals and radionuclides in environment. I think the special emphasis that Henry Tang, who teaches this course, places on is really on the classes of pollutants that are currently a priority for U.S. Regulatory agencies such as pharmaceuticals and personal care products. Also some pollutants of unidentified origin and trace pollutants of organic and inorganic origins. So again, this will be sort of a common thread through all these courses, and that's to remain as current and as practical as possible. So there is a direct transfer of the knowledge that one acquires within this program to whatever future career one might choose using the knowledge that we have hopefully provided. And if you would like to have more information on this course specifically, feel free to reach out to Henry. The email is provided there. The third course is on environmental chemistry of water, air, and soil. This course recognizes that environmental chemistry is really the science of processes that influence the composition and chemical properties of the environment and make it fit for habitation. So it will survey the behavior, movement, and impact of natural and man-made chemicals in all the layers of the environment, like soil, water, and air, in the context of atmosphere, hydrosphere, and lithosphere. So the students will understand the chemistry of environmentally important cycles. They will also analyze how the human factor affects these cycles, like acid rain, sewage treatment, ozone destruction, anthropogenic climate change, air pollution, and eutrophication. So finalist students will hopefully gain knowledge in designing and evaluating solutions to current and future environmental problems that we may face based on the knowledge that they have gained. Again, this is a course designed by Henry, and his contact is on the slide. Now we're getting into the last two, which are more focused on the green chemistry aspect. The first course is green chemistry processing. This course introduces the basic design principles for greener chemical technologies through a survey of widely used practices to green industrial synthetic processes such as catalysis, use of renewable starting materials, minimization of energy inputs, and the use of greener solvents. This really will set the stage for the next component of the next part of the course, which is to set an interdisciplinary intellectual framework for understanding and evaluating the challenges and trade-offs that are chemical industry faces in attempting to shift production processes towards renewable technologies. So the students will gain understanding of the numerous social and technical factors that then can promote or really impede, in some cases, the adoption of greener solutions, and they will systematically evaluate the impact of chemical processes on the environment. The course material will be based largely on case studies, and Professor Vuchkova is the one who has designed this course and will be teaching it. And the latest that I have is that this course will be taught this coming fall, along with the course on energy. That was the first one that I introduced. The last but not least is the course in that I'm familiar with. That's the course in green toxicology, or more specifically, chemical toxicology and the rational design of safer chemicals. Here, I think we recognize that the goal of green chemistry is to promote the adoption of safer and more efficient chemicals, products, and processes, but really in order to design inherently safer chemicals ab initio, or from the beginning, or even to redesign existing chemicals, it is important to understand what the basic principles are that dictate toxicity and environmental fate. So this course will introduce the basic tools and paradigms of toxicology, with a focus on strategies to design safer chemicals that maintain their desired function. The tools that I'm speaking of will be applied, during the course include, for example, the use of medicinal chemistry principles, computational methods for prediction of chemical reactivity, in silico predictive methods for toxicity, which are called, or most commonly referred to as computational toxicology, and include quantitative structure-activity relationships, or QSARs, expert systems, and read-across approaches. We'll also use something that really hasn't been established in the field much, but it's now emerging as a new cool application to using spectroscopic tools to evaluate chemical mixtures, and that's the use of NMR, so nuclear magnetic resonance, to predict various toxic endpoints. Now, I'm the one who has designed this course, so I can tell you that this course leverages really the most up-to-date knowledge in the field that we are aware of and we are familiar with, and some of the case studies that the students will be working on are actual research projects that are either ongoing or they have been recently published. We will also discuss the challenges and trade-offs of toxicity and biodegradability. Now, coming out of this class, the students will hopefully gain proficiency in, one, being able to effectively use the tools and metrics to evaluate and compare hazard profiles of chemical substances, and two, they will be proficient in understanding and identifying structure-function relationships with respect to chemical properties, biological activity, and environmental fate. Hopefully they will also be able to understand and evaluate the results of basic toxicology assays, and attempt a rational design of molecules so as to avoid particular types of toxicological hazard. And the idea of being able to design new molecules from basic principles is something that is not really a fully developed field, so it will be an exploration, sort of a guided exploration on the hands of the students. In that way, I feel like they will feel the appreciation of being at the forefront of the science, rather than having something that's already been established and validated, and maybe to some extent outdated. So there is that sort of a new and very progressive aspect to this course that we are quite excited about. The last component of the program is what we call the Capstone project. So toward the end of the program, so in his or her second year, each student will be required to participate in what we call a Capstone project. This experience is aimed to really provide an opportunity to identify and solve one or several real-world scientific problems. It will also enforce the interpersonal and communication skills needed to work in collaboration with other scientists and be able to translate science for non-scientists. That's something that we have realized over and over, is that as we are brought up as scientists within often very narrow focused mind, not focused minded, but focused fields of chemistry or physics, it is very hard for us to take that science and then apply it in a different context. And part of that ability is the ability to communicate and work with the people that are on the other end. For example, I was trained as a computational chemist, and for us to translate some of the computational chemistry techniques to predictive toxicology requires the ability to work with people who run cell-based assays in toxicology, and there's a training that's really required to be able to have that conversation effectively and to arrive at a common ground and solve a particular problem effectively. So we're hoping that this Capstone project will provide this sort of an experience for them and give them a head start. The Capstone is intended, it can be an individual exercise, but it's really intended as a group-based project with a partnership with an external partner or a client. It could be a government agency or a not-for-profit group, or it could also be a research project in the laboratory of a faculty member of the chemistry department. So the focus can be academic, it can be an industry-based focus, or it could be done in collaboration with a governmental agency. The group projects will require students to engage in research and apply the multidisciplinary knowledge that they have gained or acquired during their program of study to a real-world scientific question that relates to environmental or sustainability issues. The students will work in small teams and will be mentored by both the external partner of this Capstone project as well as the program director. We are hoping that the project deliverables will include a written report at the end and a formal presentation of the research results to both the external client or the external partner and the faculty that's part of this master's program. The other objective, I suppose, with this Capstone project relates to our original intent for the program, and that relates to career possibilities for its graduates. So we are hoping that this project will get each student a foot into the industry that they may want to pursue a career in, sort of like an internship, but with our academic backing. So in some ways, we leave it largely up to the students to select select their external partner and to design their Capstone project, although of course it has to be approved by the program director. So I mean, there are literally infinite number of possibilities of what the students might pursue. For example, we have some prospective students who want to work in mainland China to help study air pollution in Shanghai and how we can deal with it in collaboration with one of the private sector industries there. So there are no geographical restrictions either, although we have a network of partners that we have in DC that would be particularly suitable, but it's really up to the group of students to decide. So on this slide, I'm including some of the partners that we have discussed this Capstone project with, and who have divisions or groups that are open to working with students on these projects. Within the governmental agencies, it's the Environmental Protection Agency, it's Department of Energy, FDA, NIH, NIHS, some of the NGOs around, and some of these are not in DC, so that would require either travel or teleconferencing. It's the Environmental Defense Fund, Environmental Working Group, Natural Resources, Advancing Green Chemistry, CPA Clean Production Action, PIS NGO, or the UMass Lowell Center for Sustainable Production. In the private sector, Seventh Generation, Dow, DuPont, Doc Services, Cybera, among others. For industry groups and roundtables, the GC3 Council, American Chemical Society, Institute for Green Chemistry, as well as we have some academic partners. So if one wanted to carry out an academic research, but for whatever reason it wasn't possible with some of the faculty members here at GW, then we can work with the Berkeley Center for Green Chemistry, Yale Center for Green Chemistry, or Green Center Canada. With all three, we have very close relationships where in the past we have exchanged students or collaboratively worked on research projects. Now, this is, I suppose, we have time to talk a little bit more about one of the core courses, and that's the one that I think is, from my perspective at least, it's probably the most exciting because it's very novel. It's something that really is not taught anywhere as far as I can tell, and that's the course on chemical toxicology and rational design of safer chemicals. And the reason why it's so unique is because the field around it is really not fully developed. So for that reason, the lecture reading will be drawing on several texts as well as using recent publications in this area to build relevant case studies. So from the text we will use Chasing Molecules by Grossman, Mechanistic Toxicology, Cradle to Cradle, Professor Vuchkova's and Paul Anesta's book on designing safer chemicals, which is part of the Handbook of Green Chemistry series, and to have some introduction of in silico toxicology or predictive toxicology, Mark Cronin's and Judith Madden's latest account. Naturally, this is more text that can be handled within a course, so it will be sort of taking snippets of the material here and there to put together a cohesive storyline for the students. The learning objectives in more detail for the course are to understand the toxicological impact of the chemical industry in a historical context, and be able to use various toxicological data for hazard assessment, as well as use mechanistic toxicology to identify relevant features in chemicals and then link them to biological effects. They will also understand or learn how to understand the tenets of risk assessment, how to distinguish between hazard and exposure, and the basic principles of life cycle analysis. We'll introduce computational tools and various metrics that can be used to evaluate and compare hazard profiles of chemicals. And finally, we will explore some of the design strategies that can be used to either design chemical structures from the ground up or redesign existing chemicals that are safe, and I use safe in quotations mark, again safe with respect to several one toxic endpoint, yet they retained whatever the desired functionality was. So if we're talking about a dye that may be toxic to aquatic species, then we're hoping to redesign that particular chemical so that it still performs as an acceptable dye, but it no longer poses a hazard for aquatic environment. So it has a minimal biological activity. In more detail, the course is described here. So I think we will start with the first time this, I should say, I'm talking in future tense. The first time this course will be taught is in the spring, most likely. So naturally, it's still in preparation, but it will begin with the description of the chemical industry and some of the case studies of chemicals of concern which are well known historically, such as BPA, phthalates, and more recent flame retardants. We will then move on to discussing and introducing mechanistic toxicology, focusing on the modes of action of various chemical classes. Here we will talk about alkanes, alkenes, alkynes, about epoxides, about benzene, about polyaromatic hydrocarbons, polybrominated aromatics, just to sort of select a few classes. Then we will sort of introduce some of the general principles of toxicology as they may be presented in a format that's accessible for chemists. So we'll talk about the general principles of dose-response curves, statistical methods. We'll discuss the importance, both historical and current, of mechanistic toxicology. What can toxicokinetics and toxicodynamics tell us about the fate of a chemical and its final toxic effect in vivo. We'll talk about toxicogenomics, ADME, so the absorption, distribution, metabolism, and excretion of chemicals, and finally about ecotoxicology. The next section deals with the types of toxicological data that we typically encounter. So we'll have an overview of the types of toxicological testing, looking at models, tools, terminology, distinguish between what it means to have an acute versus a chronic endpoint. For the endpoints, we'll look both at in vivo assays of fish, in vivo assays of small mammals, assay tox models. We will look at data sources and data quality. This is something that we have been researching quite recently, actually, and it's a very important subject, both from a perspective of someone who designs new chemicals or builds predictive models for toxicity of chemicals, or simply makes decisions based on existing data on chemicals, whether to allow a certain chemical, to ban certain chemical, put it on some sort of a restrictive list. Data quality is often overlooked, and it can have a tremendous impact on the final decision or the final model. We will have an overview of non-animal tests, so cell-based assays, in vitro methods. We'll talk about high-throughput screening, and it follows that we discussed EPA's or NCCT's ToxCast system and other data sources that are available. And again, ties back to the discussion of data quality. So in utilizing or reviewing these databases, one has to always take into account where the data comes from. And based on the data quality that we may be able to assess, we can have an understanding of what we can use the data for and what its limits are. The next section deals with risk assessment and compares risk assessment to alternatives assessment. So we'll discuss hazard versus exposure, what really is risk assessment, what are the steps in a risk assessment, sort of the same process then for alternatives assessment. We'll define a chemical hazard assessment, and then we will segue into talking about data gaps which exist for existing chemicals, and that sort of brings us into the next section where we talk about predictive toxicology or computational toxicology and modeling, and how we can use those tools to fill in those data gaps that we have from experimental studies. So we'll talk about QSARs, or quantitative structure activity relationships. We'll talk about computational methods that could be borrowed from other fields like computational chemistry or computational biology to predict toxicity. We'll talk about expert rule systems and read-across approaches. We'll focus then briefly on regulation and policy, mostly on EPA and TSCA and REACH program. We'll talk about pesticides and chemicals in food and cosmetics in the context of some of these legislative programs. The next section discusses global hazards. Then we'll focus on chemicals in water, and then of course we do need to mention nanotechnology. So we'll talk about the modes of action of nanoparticles, the evidence of toxicity of these nanoparticles, and how we might go about designing a safer nanoparticle. And that, again, is a segue for the next section and the last section, which deal with approaches for designing safer chemicals, where we would focus on bioavailability, mutagenicity, and some design guidelines for minimizing aquatic toxicity. So I had a case study prepared, but I don't think we have time to go through it. But it's essentially a small sort of a few slides, a storyline of how we can take one chemical. In this case, the chemical is as a flame retardant. It's a triphenyl phosphate, and then not only we can assess it both experimentally and computationally for a particular toxic endpoint and determine that it poses or not poses certain hazard, we can then go about finding analogs and assessing those again computationally and spotting some structural trends that may help us redesign this chemical even further or suggest a completely brand new analog of a flame retardant that may be both functional but won't pose a risk, or I should say hazard, in the context of a particular toxic endpoint. And we can do this sort of on a general level or focusing on a specific, in this case, the toxic endpoint that we're discussing in this case study as acetylcholine esterase inhibition. So I think I will skip through these slides. Again, the case studies on designing safer chemicals for this course will be introduced late in the semester after the students have been exposed to not just the basics of toxicology but also the basics of computations in the context of toxicology. So they will have all the tools necessary to not only follow the case study but to sort of answer some of those questions that arise along the way. I think the last thing I want to show is some of the general requirements, admission requirements for the program, so the more practical specifics for those interested. So students have to submit GRE scores. It is required that students or professionals who want to enroll in this program have a bachelor's degree in science or engineering with a GPA 3.0 or above. We do require, although there is some flexibility on a case-by-case basis, but in general we do require that the candidates have completed 2 semesters of general chemistry, 2 semesters of organic or inorganic chemistry, and 1 semester of quantitative or instrumental analysis is recommended. Again, there is a flexibility around these, and but naturally, since this is a science-heavy program and it's focused on chemistry, a solid foundation in the field from undergraduate studies is presumed and required. Some of the supporting documents that we require include, of course, this is very standard, they include official transcripts from all post-secondary institutions that the candidate has attended, 2 letters of recommendation, resume or CV, a personal statement, and for international students, we do require TOEFL or IELTS scores. So our departmental website, again, the program is housed by the chemistry department, so there's a direct link on the departmental website with the application with a lot of the details I probably forgot to mention today. The application deadline for the fall semester is already passed. It's April 1st, but we do take applicants for the spring semester. The deadline for that is October 15th. It's a master's program, so it's a paid-for program, but there is financial aid, which is awarded based on merit. Again, the link is provided on this slide. And if there are any further inquiries, then for some of the general questions about the program, our department chair would be a good person to touch base with, or myself, or Professor Vuchkova as well. If you have any specific questions on some of the courses that I introduced, especially the one that I am, so my focus is more on the green chemistry aspect, so the latter of the course is the latter 2. I would recommend touching base with the folks that I mentioned on each of the slides. See if the course covers what you might be interested in. And that's all I have. So thank you for listening, and of course welcome some questions.
Wonderful. Thank you so much, Jakub, for a wonderful presentation. That's really interesting and sounds like a fantastic program. And just this is brand new, and so will this fall be when you're welcoming your first cohort of master's students? Is that correct?
That's right. That's right. So the first classes start this fall, and the first students are enrolling. They have already enrolled, but they will be starting this fall.
Great, great. And have you had a good response so far?
Yes, we have had, so we do, again, it's at the beginning, we try to be a little more careful with how many students we accept since the program will sort of be starting slowly. So we have been very selective, I think, the first year just to be on the more cautious side, but there has been definitely a response that's been very positive, and we're hoping that that's going to increase as we go through the next few years.
That's fantastic. So if you have a question, everyone who's listening in, just type a question right into the question box here. I've got a couple here that I'll start with. And I should also mention our winner of the Green Chemistry book is Judy York. So Judy, you'll be getting an email from me, getting your contact information. But for Jacob, we have one that's, are any of the materials used in your course, which it sounds like, I think this question came in before you went into more of detail, but are any of the materials used in your course on green toxicology available to share?
So currently there aren't any, but again, there will be, we are hoping that there will be an online resource paired with this course. There will probably be something that's available for the general public, but of course a majority will only be available for the registered participants. But as of now, since the program is starting in the fall, there is no such thing.
Yep, okay, great. And another question, can you recommend, so I think this has to do with your own personal expertise here, but can you recommend one computational tool or piece of software that is useful for students to predict toxicity of chemicals and use in the design of greener chemicals? So I think they're looking for, if sounds like if you could pick one tool, what would you recommend?
Well, that's a very broad question. I mean, even if I strip the designing component from it, just to be able to predict would depend on the toxic endpoint that we are looking at. There's a plethora of tools, and they all have their strengths and weaknesses. I think I'm going to be a little selfish here, but I mean, we have published. I can send that publication to you, and maybe you could disseminate it then to the participants. We have published some sort of a general design guidelines, which can serve as sort of a predictor as well for aquatic toxicity. And aquatic toxicity is not really an endpoint. It contains a variety of endpoints, and because of its sort of non-specificity, it captures general reactivity, which is, you know, a trigger where a lot of xenobiotics would act as electrophiles and bind biological targets, and that would sort of then turn on the cascade of events leading to a variety of toxic responses. So that's one aspect that these guidelines capture, and the other one is bioavailability, so how likely it is for the chemical to actually enter the organism. So a combination of these two very generic indices can provide some useful guidance as to is this chemical going to be generally toxic, or is it not? So I think that's a good place to start.
That's fantastic. I know there's a lot of interest in this topic, and I have a question for you. I know that there's a lot of work that you guys are collaborating through a network called, or a group called Modern, and I was wondering if you could just explain that briefly and talk a little bit about the resources that will be coming out of Modern, because I know that will be of great interest to the green chemistry community.
So I'm actually, as of now, somewhat tangentially, I mean, not really directly involved with the Modern research, but it's a collaborative between Baylor University, George Washington, Washington University in Seattle, and Yale University. And the idea was sort of to create a robust paradigm for assessing oxidative stress, which is one of those very complex set of pathways that is very difficult to deal with, because it just involves so many overlapping adverse outcome pathways, or so many overlapping mechanisms that it's very hard to model, and it's very hard to study with cell-based assays too. So that's sort of what the collaborative started around. As of now, I think there are advances in in some chemical classes as to having some guidelines or basic predictive models for determining whether a given chemical may cause oxidative stress with some level of probability. But there is you are absolutely right, there's an educational outreach or educational aspect of this, which is mostly handled by University of Washington. But I can rather than make up stuff on the spot, I can probably send you some of this information, which then can be forwarded. Yes.
Wonderful. That's great. Okay, well, that's what I have for questions for you. This has been fantastic. So thank you so much, Jakub, for a wonderful presentation and for giving us some ideas, for around this program. So it's really, really a unique program, and I think we can all take some lessons learned from that and some inspiration from it as well. So thank you so much.
Absolutely. Absolutely. And again, if people have any questions and they want to reach out to specific faculty, this is a small department, and everybody here is very excited about this new program, so don't be shy.
Yes, awesome. That's wonderful, and that's a wonderful thing about the green chemistry community. Everybody's so helpful. So, and thank you to everyone for listening today. All recordings and supporting documents are posted on the link that you see here. The recording will be posted by the end of the day today. We do take the summer off for webinars in particular, but there's lots of upcoming events for learning more about these topics and other green chemistry related. So there's several conferences. The two that will be at are BCCE and the ACS Philadelphia. At BCCE, we will be running a Toxicology for Chemists symposium and workshop, and some of those modern collaborators that out of Washington State in Baylor will actually be collaborating with us on both the symposium and workshop. So if you're out at BCCE, come and see us. And thank you again for tuning in, and we'll see you next time. Thanks.